going here. Let's see. Here we go. Alright, so we're going to look at section 9.8 today, and maybe section 9.9 if we have time for that. I would like to look at 9.9 today. We'll see how it goes, though. Are there any questions over 9.7, first of all? Okay. Alright, so section 9.8 is on power series. Alright, let's look at the definition of a power series first. It says if x is a variable, then an infinite series of the form look at the sum as n equals 0 to infinity of a sub n times x to the n is equal to a0 plus a1x plus a2x squared plus a3x cubed, and so on, is called a power series centered at 0 specifically. Okay. If it's centered at C, then we have the sum n equals 0 to infinity of a n times x minus c to the n is equal to a0 plus a1 times x minus c plus a2 times x minus c squared plus a3 times x minus c cubed, and so on from there. Okay. The point being that, we either have x or we have x minus c. X minus c is more general because it has a generalized value for c, but it could be centered at 0, in which case, if c is 0, that's just x. So, and then we have this coefficient expression a sub n. Now, the Taylor polynomials we looked at are sort of a power series. They're not technically infinite, so it's not technically an infinite series. Well, it isn't an infinite series. But it was somewhat similar in that regard because we still had the x to the n term, but we had a very specific expression for a sub n, which was the nth derivative of f evaluated at c divided by n factorial. So we're going to look at, in section 10, Taylor series instead of Taylor polynomials, and we'll see that it's specifically a form of power series with a a particular definition for a(n) in that case. So that's something we'll be looking at eventually also. Yeah, it'd be nice if we finished 9, 8, and 9, 9 today. We'll do 9, 10 on Tuesday, review on Thursday, and then test before Thanksgiving. That's what we should look at, or what we should expect. Anyway, I'm just thinking about the schedule at this point because we're getting close to the end. So good news, and also me making sure we get through everything. We'll have one more week after Thanksgiving. There's a little bit we need to cover out of Chapter 10, and then we'll have a day of review also. So we'll be alright. Alright. So, we may just skip Section 10. We'll see how it goes. Not Chapter 10, but Section 10. Alright, so with power series here, it's a little bit different than just the normal infinite series we're looking at, because we do have a variable expression x as part of all of this, and so that's something that we'll have to keep in mind as we continue to look at these. It is a function of x ultimately. Now, as with everything else that we've looked at, we certainly are interested in the interval of convergence, or radius of convergence, whatever you want to call it. We are interested in convergence. And so for power series, it turns out that largely this will be, there's really three scenarios that we look at for power series, and it's either the power series converges for all real numbers, the power series converges for only the center value, which is not saying much, to be honest, and then the third possibility is that there's a range of values between which the power series will converge. Okay? And what we use as a tool here is kind of a modified form of the ratio test that we looked at in Section 6. Okay, so we let f of x equal the sum n equals 0 to infinity of a sub n times x minus c to the n. That's our power series as we defined it. Okay. Okay, and so we have a ratio test for power series. And this says that we let L, do we let it be L this time? No, we don't use L this time. I'm sorry. We take the limit as n goes to infinity of the absolute value of a n plus 1 times x minus c to the n plus 1 over a sub n over x minus c to the n. Now, what we'll notice happen here is that depending on the expression inside here, it may not just be x minus c to the n, it could be like x minus c to the 2n, but I'm just giving you an example in this case. So basically we plug in n plus 1 for n, put that on the numerator, and then we divide that by the original term here, put that on the denominator. Okay. So whatever it is, if it's n plus 1 or 2n plus 2, whatever it happens to be, we'll go from there, because there are some different power series that we'll run into. But we'll take the limit of this quotient, the n plus 1 term divided by the nth term, as n goes to infinity. And the convergence is, we want to find the values of x for which this limit is less than 1. Okay. Now this is an inequality, so it potentially is for a range of values. Now it may be that the limit of this goes to 0, and if we get a 0 value, then it's always less than 1, and so the radius of convergence is negative infinity to infinity. So case 1, the limit approaches 0, so the power series converges for all x, negative infinity to infinity. Case 2, the limit goes to infinity, which means the power series converges for x equals c. Which is really not that helpful because it only converges at the center. It doesn't tell us anything at all. It should converge to the center by the very way that we created the power series in the first place. And so this is essentially a trivial case because it diverges for everything that we're interested in. Okay. Now case 3, we say we solve this all if the limit doesn't go to 0 or infinity, but instead it hits some number in between or some expression in between, then we just solve the inequality, because more than likely it'll be some expression of x in here where it's less than 1, and we solve that inequality for x. Solve the resulting inequality for x. So that's the 3 different things that can happen here when we look at this ratio test for power series. Either the limit goes to 0 and it converges for all x, the limit goes to infinity and it converges for x equals c, or we end up with an inequality to solve and we solve it. And we'll talk about that when we get to it, because it does require some different things. Ultimately, it's an absolute value inequality, which means it becomes a compound inequality. Okay, so let's look at convergence problems first, since we've looked at that. So we're going to be on page 658. Let's see. We'll start with a relatively simple one. This will be number 16. We have the sum n equals 0 to infinity of 2x to the n. So that means we have the limit as n goes to infinity, the absolute value, and now we take 2x to the n plus 1 over 2x to the n less than 1. So essentially we take this expression inside the summation, we plug in n plus 1 for n, that's our numerator, and then we just take the original term, that's our denominator, and this is the quotient that we're interested in. Now we notice that there's an absolute value function here around everything. Now the absolute value bars will get rid of any alternating terms that we have, like if we have negative 1 to the n or n plus 1, it'll cancel those out. However, we still need to keep track of them even if there aren't any alternating terms, because x itself may be positive or negative, and we don't want to discount that possibility. What happens here, in this case, we can reduce what's going on here with the x's. Like we have 2x to the n plus 1 over 2x to the n. Because we have the same base, we can combine their exponents by subtracting. So n plus 1 minus n will give us n goes to infinity, and we'll just have the absolute value of 2x less than 1. So n plus 1 minus n is 1, so it's 2x to the first power, or just 2x. Okay. Now, by simplifying that expression, we've eliminated the n value from this term. So if we take the limit as n goes to infinity and there isn't any n here, then the result of the limit is just the term that's already there, which is the absolute value of 2x. And that must be less than 1. So we have to figure out for what values of x is the absolute value of 2x less than 1. Well, the way that we kind of get rid of the absolute value portion here is that if the absolute value of 2x is less than 1, that means 2x is between negative 1 and 1. And we go from being an absolute value inequality to a compound inequality, because we have more than one less than sign here. So this means 2x is now between these two numbers. That's the interpretation of this term. Okay. Now we want to get x by itself. Now it's 2 times x, so we know we'll just divide everything by 2. And that means that negative 1/2 is less than x is less than 1/2. Okay, and that'll be the essentially give us the region where the function will converge. Now we're not going to go quite into as much detail as what the book does, because you'll notice the book, it might have less than or equal to on one of these. Probably this one would be equal to. I'm not quite sure, but it may not be either one in this case. Anyway, but we're going to ignore that. We'll just say less than, and we'll be okay with that. Because we at least know this much is true. X is between negative 1/2 and 1/2. It may also be able to equal those, but I'm trying to simplify the material a bit. Now what we would do to check that is to check the endpoints. I think in this case it's actually both less than. Because if we plugged in a 1/2 for x, 2 times 1/2 is 1, and 1 to the n is a divergent series. Because it's just a series of 1s being added together, which is infinity, I think. It'll be a little more difficult to prove, though. And same with negative 1/2. Although that one may actually... That one's kind of weird. We'd have to do like an alternating series test in that case. I don't think it works either. It's not a decreasing series. Anyway. Let's continue. And we'll look at number 20. Here we have the sum, n equals 0 to infinity. And we have 3x to the n over 2n in parentheses factorial. Now, sometimes we call this expression inside the power series as u sub n. Okay, so u sub n is equal to 3x to the n over 2n factorial. Then u sub n plus 1, we just replace each of our n's with n plus 1. So it'll be 3x to the n plus 1. This will be 2n plus 2 factorial. Again, if we replace n plus 1 here, the 2 distributes to it. So it's 2 times quantity n plus 1, which is 2 times n plus 2 times 1, or 2n plus 2. Okay. And now we want to divide those. Un plus 1 divided by un. So what I would say is we take un plus 1 and then multiply by the reciprocal of u sub n. That way we can turn it into a multiplication problem, then this division of two fractions that we would otherwise have. So u sub n is 3x to the n plus 1 over 2n plus 2 factorial times, and then we have 2n factorial over 3x to the n. And we want that to be less than 1. Now, what we kind of saw from the first example there, number 16, is that the x's, typically what's going to happen is we're going to be able to reduce these to the point that we cancel out their n. Okay? Like we have 3x to the n plus 1, and we have 3x to the n. And we know, once again, we can subtract the exponents, since they have the same base. N plus 1 minus n leaves just 1. So it would be 3x to the first power. And what we set up here is that since we were able to simplify that to where we no longer had an n, we were able to basically, this is not affected by the limit operation anymore. In that case, there is no n to approach infinity, so the limit doesn't apply to the absolute value of 2x in this case. We're actually going to see a very similar thing happen in number 20 with the 3x term. So we go back here, and we're looking at this. We know we can reduce these, we know we can reduce these, the factorial terms, and we'll talk about that a little bit more in a second. But with the 3x's, in particular, we know n plus 1 minus n is just 1, so we'll end up with 3x to the first in the numerator. And because it no longer has an n, we can actually factor that outside the limit, which is significant. So that's what I'm going to do next. One thing we might do first, just to make it a little bit easier, is to rearrange the terms so that we have them vertically over the terms that they're reducing with or simplifying with. So we might do something like this. n, sorry. So if you prefer, you might try to do it this way, where we kind of rearrange them. We know we're going to reduce or simplify these, and likewise these will somehow simplify, and that way we can kind of pair them up vertically that we're going to work with them. Okay. Now, we know here that's going to give us 3x to the first power after we simplify. And then these terms here, we have 2n factorial over 2n plus 2 factorial. Now, we know 2n factorial is 1 times 2 times 3 all the way up to 2n. On the bottom, 2n factorial is 1 times 2 times 3. We get to 2n, but we keep counting. The next number after 2n is 2n plus 1, and the next number after that is 2n plus 2. So we counted all the way up to 2n plus 2. We don't know what n is, but it's sufficiently large that we know we can look at this ratio. And what happens is all of these cancel out, and we're just left with 1 over 2n plus 1 times 2n plus 2. Okay, so we've reduced it or simplified it, however we want to call it, and this is where we're at. Now, like I said before, the 3x, since it doesn't have any ends, we can actually bring that outside of the limit. Now, remember, x can still be positive or negative, so we need the absolute value there, because that's still applying to that. However, n is a positive number, so at this point we could rewrite this and say absolute value of 3x times a limit of 1 over 2n plus 1 times 2n plus 2. We would no longer need the absolute value bars here because n is already known to be a non-zero number, or, well, at least a zero value. It's not negative, so so we're good making that assumption or making that change. Okay, then here's the issue. Now we look at our limit. We have 1 over infinity times infinity. This is 1 over infinity, which goes to 0. Okay? So now we have absolute value of 3x times 0 is less than 1, which means 0 is less than 1. Alright, because anything times 0 is 0. It doesn't matter what x is, it can be 0. So here's the question. If we get a result of 0 less than 1, what does that tell us about x? Remember what we're trying to find, though. We want to know for which values of x is this true. For which values of x is 0 going to be less than 1? It's kind of a silly question. 0 is always less than negative 1. There's no value of x that's going to change that. So basically, once we know we have was essentially a statement that's always true. In logic, we call that a tautology. Just throwing out some extra knowledge there. I don't know. If so, we have something that's always true. Then that means that it's going to be true for any real number x, which is negative infinity to positive infinity. So x may be between negative infinity and positive infinity because it doesn't matter, because x basically canceled out of this and it resulted in an always true statement. Okay. Right. So that one, basically that was case 1. The limit went to 0, so the power series converges for all x, negative infinity to infinity. The first problem, we actually had to solve the resultant inequality, so we actually got our interval there. And the other possibility is that the limit already goes to infinity, so it will never be less than 1 in that case, except at x equals c. So that's our 3 cases there. We've already looked at problems for 2 of those. Now, how would this be shifted around to where it would end up being case 2, the one we haven't looked at yet? Well, that would occur if we basically invert this term that we're looking at. If we were to have our factorial be on the numerator and then our other term exponential on the denominator, then we would say, okay, that's going to go to infinity as a result instead. What happens is we end up with this term with the factorials on top instead of on the bottom, and if they're on top, infinity over 1 goes to infinity, not 0. And that's the other outcome that we could have. We don't see that as much, but I wanted to mention it. I want to look at problem 28 also. I think this one is not centered at 0, so it has a little bit more interesting things going on. The terms involved are a few more terms involved here also, which I think will make it interesting too. Just to see how everything interacts and gets dealt with. So negative 1 to the n plus 1, x minus 2 to the n, and then on the bottom we have n times 2 to the n. Now, this is basically u sub n, we'll call it, and we want the absolute value of u sub n plus 1 over u sub n. Now when we take the absolute value, that's going to get rid of our alternating term here, this negative 1 to the n plus 1. So we don't really need to worry about that term. We need to focus on the x minus 2 to the n over n times 2 to the n. So absolute value of u sub n will be absolute value of x minus 2 to the n over n times 2 to the n. And the absolute value of u to n plus 1 will be the absolute value of x minus 2 to the n plus 1 over n plus 1 times 2 to the n plus 1. Okay, by taking the absolute value, we get rid of the alternating term, because this value that's either negative 1 or positive 1, depending on the exponent, if we take the absolute value, it's always positive 1, and we don't need to write it down if we're multiplying everything by 1. Okay, so we set up our limits, n going to infinity. We do un plus 1 times the reciprocal of un, like we've been doing with our ratio test, going back to section 6. X minus 2 to the n plus 1 over n plus 1 times 2 to the n times, and we'll put the reciprocal of un, which is n times 2 to the n, this is plus 1, sorry, over x minus 2 to the n, less than 1. The reason we automatically include less than 1 here is we go back to our ratio test. It only converged if the ratio was less than 1, or the limit of the ratio was less than 1, and so it's really the same principle here. We're not interested in whether it converges or diverges. We want to know when exactly it converges, because with the variable x in here, it opens up some different possibilities. Alright, but then we notice here we basically have three different types of terms. We have our x minus 2 terms, we have our polynomial terms n and n plus 1, and we have our exponential terms 2 to the n and 2 to the n plus 1. So if we like, once again, we could arrange those vertically from each other. X minus 2 to the n plus 1 over x minus 2 to the n times n over n plus 1 times 2 to the n over 2 to the n plus 1. And we can reduce each of those individually if possible, and then go from there. So we know that we can reduce here because these are the same term being raised to different exponents, so we can just subtract their exponents. N plus 1 minus n just gives us x minus 2 to the first. Now n over n plus 1 cannot be reduced. Remember, this is a polynomial. This is basically a rational function of polynomial terms right here. And we cannot simplify here unless we have a common factor on top and bottom. And we haven't factored these at all, so they're not the same, so we cannot reduce them. I know a lot of students, especially my algebra students, really want to try to reduce those n's, but it's just not possible. Okay. Even though they technically don't reduce, we'll end up seeing a similar thing happening, but we'll talk about that. Same thing here as what we saw in the first term, so it's the same base with a different exponent. So we can just subtract the exponents once again. Now, what's different here from these first two terms is that the larger number is now on the bottom, so that means we'll have an extra 2 to the first, but it'll be on the denominator instead of the numerator. Okay, so that's what we're looking at. Now we know from our previous examples that this first term, x minus 2 to the first, or just plain x minus 2, it's no longer affected by n, so we could just factor that out of the whole thing. Likewise, we could take the 1/2 out if we want to, because it no longer has an n involved in that expression either. So we could take x minus 2 here over the other 2 there. It's still in the absolute value bars because x may still be positive or negative. And then inside the limit, we only have n over n plus 1 remaining. Sorry, off the screen. There we go. So we can take our x minus 2 over 2 and just bring it outside the limit, still inside absolute values because of the x. N over n plus 1 is the only thing left inside. Now, this limit here, n over n plus 1, we know this is infinity over infinity, but again, we can use our shortcut here if we want because they're both polynomial terms, or we could just simply use L'Hopital's rule. But ultimately, the limit here is 1. It's n over n. These are identical variable terms, and so we just take their coefficients as the limit, which is 1 over 1, which is 1. So what does that leave us with? Well, we still have our absolute value term, and that has to be less than 1. So I'm going to bring that back up here. We have the absolute value of x minus 2 over 2 is less than 1. Now, much like we did on the first example, we'll go ahead and instead of using the absolute value inequality, we'll convert that to a compound inequality. So if the absolute value of this is less than 1, that means this value inside the absolute value bars must be between -1 and +1. sorry. So we end up with -1 less than x minus 2 over 2 less than 1. We'll go ahead and multiply everything by 2. That'll get rid of this 2 on the bottom. So -2 less than x minus 2 less than 2. And we can add 2 to everything to make that 0 less than x less than 4. And now that's our interval of convergence for this particular power series. It can only converge between 0 and 4. It may actually work for 4 also, so it may turn out that if you look at the answer in the back of the book, this is an equals to, but again, we're going to skip that for now. Okay. This is still a step-by-step process. There's a little bit more stuff for us to pay attention to, and now we're working with these absolute value inequalities, which are not terrible, but if you haven't worked with it a whole lot, it can be a little bit rough. But there we are. All right. Let's see what else I need to cover here. There is one other topic that the book brings up in this section that I would like to cover, and that is the derivative and integral of a power series. Okay. So, to begin with, we go back to our basic power series definition. Remember, I wrote it as f of x equals the sum n equals 0 to infinity of a sub n times x to the n. Now, we could put the x minus c to the n since it's generalized to be at center c. I think I want to use just the center being 0 to illustrate the derivatives and integrals because that will make it a little bit easier as a result. It doesn't really change it too much, it's just a little bit less writing, I guess, is what it amounts to. Anyway. So that's f of x. And if we want to differentiate the function, f prime of x, then remember our main variable is x. We've got a lot of stuff here that's not x. We have n going from 0 to infinity, and we have this coefficient expression a sub n. Those do not depend on x, so they're not really affected by our derivative operation for the most part. So mainly we're just going to differentiate this x to the n term. So we think about what is the derivative of x to the n. It's like a power rule. It's n times x to the n minus 1. Okay. There we go. Now, so we differentiate this term, n times x to the n minus 1. I go ahead and put the n in front of the a sub n. It's not a huge difference, but that's the standard order we tend to do it in. Now there is one thing we have to worry about here now, though. The power series is basically an infinite polynomial. If we were to look at the expansion of the terms, we look at the expansion of the terms. Here's a0 plus a1x plus a2x squared, and so on. I should probably write one more term, and then we'll do dot dot dot. Okay. So that's what we're looking at. Now, because this is an infinite polynomial, that means all of our terms must either be a constant or have x raised to a positive value. That reason I bring up that particular issue is we notice that if we left this first value here as n equals 0, if we plug in n equals 0, we get x to the minus 1. X to the minus 1 is a rational term, it's not a polynomial term. Remember that x to the minus 1 is 1 over x. And we don't want that to be in our power series. It cannot be part of our power series. The other issue is if we plug in n equals 0, this is just going to zero out the whole thing anyway. So whenever we differentiate just a basic power rule operation like this, excuse me, we go ahead and increment the starting index from n equals 0 to n equals 1. That way, when we look at this answer now, if we plug in n equals 1, we get 1 a1 x to the 0, which 1 and x to the 0 are both 1, so it doesn't really, we just have a1 there. And then for n equals 2, we get 2 a2 x to the first. And for n equals 3, we get 3 a3 x to the second. And so on. But now we look at this. We essentially took the derivative of this expression and we came up with this expression. And we can see, if we were to differentiate the individual terms here, a0, the derivative is 0, because that's just a constant. a1 times x, the derivative is a1, because a1's our coefficient and x is our variable. a2 times x squared, the derivative is 2 times a2 x to the first, because again we're doing a power rule there. And then the derivative of ax, a3 x to the third is 3 times a3 x to the second. As you see here, and it just keeps going from there. So whenever we differentiate, unfortunately this won't be all the time, but most of the time we'll increment this to n equals 1. It partially depends on what this expression actually is. Now the expression we have here, absolutely we would increment from 0 to 1. Okay. Increment means add 1. So, sorry. Because otherwise, if we plug in n equals 0, we get that x to the negative exponent term, which we don't want to have. However, depending on the power series, if n equals 0 would not result in a negative exponent, then we would want to leave it there. And in that case, we would not increment the starting value. We'd just leave it n equals 0 to infinity, and then we'd still have our derivative inside. That only applies if plugging in n equals 0 doesn't make this a negative number. In this case, n equals 0 does make this negative, so we want to make sure we leave it out. We don't want to have a negative exponent. That's essentially what's happening here. Okay. Let's take another derivative of this. We'll get the second derivative. So f double prime of x. Now, as you might think, we already increment this once, so when we take another derivative, we'll increment one more time to 2. Okay. We have an n, and then we want to differentiate x to the n minus 1. Again, this is a power rule derivative, So we multiply by the exponent in front, n minus 1. We still have an, but now we'll reduce this exponent by 1, so it'll be x to the n minus 2. And again, if we look at the expansion of this power series, starting at n equals 2, we get 2 times 2 minus 1 is 1, so 2 times 1 is 1, or 2, sorry. A2, and then x to the 0, which is 1. N equals 3 would be our next term, so 3 times 2, which is 6. A3, x to the first, and so on. And we notice how our terms here continue to be the derivative of the terms above. The derivative of a1 goes to 0. We no longer have that term. The derivative of 2a2x, well, x goes to 1, so it's just 2a2. And then the derivative of 3a3x squared, the derivative of x squared is 2x. Bring the 2 with the 3, so it's a 6. And then we have a3 and then just our x. So it agrees with what we already know should be true, is that the derivative of f prime is f double prime, and that should apply whether we're looking at the power series definitions or if we're looking at their expansions. The other question is, how would we integrate f of x? Well, the integral is applied the same way we did with the derivative, in which case we're integrating x to the n. So if we integrate x to the n, it'll be x to the n plus 1 divided by n plus 1. That's just our power rule for integrals. We don't have to change the starting index on an integral, because if we plug in n equals 0, it's still x to the first, which is a valid polynomial. It's only if that drops to a negative number where we have an issue, and we change the n based on that. So now, there will of course be a plus c there because it's an indefinite integral. But we could also do a definite integral there if we wanted. Let me show you now some of the common power integral, or common power series. Not power integrals. Sorry about that. This is where I miss having a whiteboard where I can just immediately erase my mistake and rewrite the word properly. Instead, I can't use pencil because it doesn't show up as well on the document camera I'm using. So we're stuck with pen, unfortunately. Anyway. E to the x, we talked about this a little bit last time, but it's n equals 0 to infinity of x to the n over n factorial. So the expansion of e to the x is, and these are centered at 0, by the way. I guess I should mention that. It's 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so on. It actually is something that we could easily do with a Taylor polynomial or Taylor series, similar to what we looked at in section 7 last time. Let's look at sine x. This is an interesting one, and we haven't discussed it previously. This is -1 to the n or n plus 1? I'll figure that out in a second. X to the 2n plus 1 over 2n plus 1 parentheses factorial. The first term should be a positive x to start off with. Okay, I've got it right then. Yeah, so it'll be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. Sine x actually has a lot of the terms similar to e to the x. It's basically the odd terms, but also alternating positive to negative. Cosine x is actually very similar to sine x in its definition. It's negative 1 to the n, x to the 2n over 2n plus 1, or no, 2n factorial, my bad. Notice that we have 2n plus 1, 2n plus 1, and then 2n and 2n here. And so cosine basically gets the even terms of the e to the x series, but again alternating positive to negative. Because of that relationship, I hesitate to go into this any further. Because of this relationship, if we combine these together, we kind of get e to the x, but not exactly. It turns out to be the basis for Euler's formula, which we'll study in differential equations, which is actually a formula from complex number analysis. It doesn't involve I. Let me just tell you that much. Anyway, so there's kind of a relationship there, but not exactly. Let's see, some other common ones. Natural log of x plus 1 is another one that we sometimes identify. Interestingly, it starts at n equals 1 instead of n equals 0. Largely because natural log of 1 is 0. That's kind of the foundation of that. Gosh, I forgot what the series was. I'm going to have to look it up. It doesn't have a factorial. I think it's just x to the n, or it might be x plus 1 to the n over just n. Let me look it up, though, before I go too much further. This might actually be in section 10, I'm trying to find. Yeah. There we go. Oh, it's alternating. I forgot that part. Goodness. Negative 1 to the n plus 1 x to the n over, oh, this will be n, no, it'll just be n, yeah. I think that's right. Anyway. The book has the series for natural log of x. I prefer writing it as natural log of x plus 1. I think, well, okay, they centered it at 1. That's part of the issue. And I centered mine at 0. So it's really a translation of what they did. But I think I have it right down correctly. It does start off as a negative. Well, actually, no, the first term is positive. So if we look at the expansion, it's actually positive x and then minus x squared over 2 plus x cubed over 3 minus x to the 4 over 4, and so on. It no longer has a factorial on the denominator like those first three functions do. Instead, it's just an increasing standalone number, which is different. Yeah. Yeah, and in fact, if we let me just show you this page now. They didn't actually give it to you written as a summation, but they gave you the nth term, which is basically what's going to be inside the summation. Like for sine, it's negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. There's cosine, same as what we wrote down. Then it also gives e to the x, which I gave you that one already, and then natural log of x, like I said, which is a little bit different than natural log of x plus 1. I did a translation on that. 1 over 1 plus x is actually closer to the natural log of 1 plus x or x plus 1 because that's the derivative. Which means I should have x plus 1 on top. Oh, no, we're okay. We're okay. Yeah, sorry. Blanked out for a minute there. New series for 1 over x, and arctangent, arcsine. Actually, arctangent looks a lot like... Oh, sorry, you can't see it there. Arctangent looks a lot like the sine series, except it doesn't have a factorial. Arcsine is very different, as we can see with the products it has in the bottom. And then we have what's called a binomial series, 1 plus x to the k, and it does some weird things because of that. It actually, it's easier to define the expansion of 1 plus x to the k if we've done any work with combinations and statistics. There's some benefit there as far as ease of writing that expression, but it's okay. We'll be alright. Anyway, so those are some of our common power series. We could also do hyperbolic cosine and hyperbolic sine. That's actually, hyperbolic sine would be the same thing as sine, but without the alternating term. So I could write that one down. So hyperbolic sine of x will be n equals 0 to infinity of x to 2n plus 1 over 2n plus 1 factorial. And then hyperbolic cosine will be sum n equals 0 to infinity of x to the 2n over 2n factorial. Notice that hyperbolic sine plus hyperbolic cosine is essentially e to the x, which is the formula that exists. Because this gives us the odd terms of e to the x, this gives us the even terms, so combined together gives us e to the x. Okay. When we say hyperbolic sine, that's actually a function of e to the x. It's e to the x minus e to the negative x over 2. Hyperbolic cosine is actually equal to e to the x plus e to the negative x over 2. So when we add them together, we just get e to the x. So it all kind of reduces nicely. But we can see that definitely happening by looking at the expansion of the terms here. If we were to add these together, we get all the even terms and all the odd terms. Just gives us all the same terms that e to the x has now. These come in handy. Like I said, Euler's formula, which we'll talk about in differential equation, is based on combinations of these power series, e to the x, sine, and cosine specifically. And that gives us some interesting results, and is pretty useful for what we do there. Other than that, we don't see a whole lot of power series outside of approximation methods, unless you end up majoring in like math specifically, and you go into a lot of the theory that's based on this stuff. It's a little tricky at that point, but it's interesting if that's what you are, the path that you're following. So. Okay. Also, a lot of, I don't want to sell it short, a lot of engineering majors utilize series to an extent. There's a lot of series work in electrical engineering in particular, but less so in some of the other disciplines. But depends on what you're doing. Okay, let's see where we're at here. I'm thinking it's not strictly necessary for us to cover 9.10. I've already covered part of it here, just talking about these common power series. So I may leave it at that, and then we'll do 9.9 on Tuesday, and then review Thursday next week. What I'll go ahead and do is post a review or practice test online, so if we wanted to start working on that, we could. I think I have one ready to go, and so I'll probably go ahead and do that, and yeah. Let me give you a few of the 9.8 problems for homework, so you can practice the convergence and divergence of power series. Let's see. A little bit off screen. There we go. Page 658. Go ahead and look at 15, 17, 19, 23, 25, 25, that may be the last one. Go ahead and throw in 29 in that, and I think that'll be good. So I would say go ahead and practice those 6 at least. That we didn't really utilize the integral or derivative of power series today. However, we will use that in section 9.9 when we approximate the value of definite integrals using power series. So that is something that we will do on Tuesday when we continue. So I think we'll go ahead and stop there. So, y'all take it easy. Have a good weekend, and I'll make sure I go ahead and post the review. That way, if you want to start working on it, you can. But we will work on it in class on Thursday next week. That way, sorry. That way we'll be able to have our test basically be from Tuesday after class. Well, actually from, what did I just say? From basically after class next Thursday through all of Thanksgiving, and then through Monday night after Thanksgiving. So that'll give us a little bit longer to take the exam, but it does go across Thanksgiving, so I would encourage you to finish prior to Thanksgiving. It also means that we won't have a formal class on the Tuesday before Thanksgiving, because that'll just be your opportunity to take the test during class time. So utilize that, and then we'll have 2 days of class after Thanksgiving, and then we'll be finals week, I think. I'm pretty sure that's where we're at. So we're closing in. Almost done with this thing. So that last week after Thanksgiving, I'll have 1 day for new material, and then we'll spend 1 day talking about the final exam and what we can do to review for that. Because I actually have a review you can work on for that, and we'll go from there. So you'll have a good rest of the day, good weekend, and I'll talk to you next time. Bye.